任何科学技术的发展和进步都离不开两个主要的推动力量，一个呢是科学研究，另外一个是工程实践。这两者是相互补充、相互促进的关系。科学研究主要考虑的是做什么，而工程实践主要考虑的是怎么做。这两者其实并没有高下之分。比如呢，我之前在公司里就担任芯片工程师，主要就是做工程设计和验证高性能的电路和芯片架构，让云数据中心里的数据传输更快、更稳定。现在我来到中科院计算所担任副研究员和硕导。那么作为一名科技工作者，日常工作就是做前沿芯片技术的探索和研究，比如如何更快地发现芯片设计中的潜在漏洞，让芯片开发的过程更加的高效快捷。那么这个方向叫做芯片的敏捷验证，这个也是当前国际上非常前沿的领域。过去一段时间我就带领几位实习同学围绕这个方向做了一些微小的工作，取得了一些前期的进展。我们把这些成果总结成论文，作为 full paper 发表在了2023年的 FPGA 大会上。我在大会报告的录像也放在了这个视频的后面，供大家交流探讨。那么在报告之前，我想先花2-3分钟的时间，简单介绍一下 FPGA 领域的主要国际会议都有哪些，那么我们这个研究工作主要取得了哪些成果。今天这期属于聚焦芯片前沿研究的内容。如果你对这些偏前沿和学术的内容不感兴趣也没关系，我还有很多科普的视频可以去看看。那么先简单介绍一下FPGA 领域在国际上主要有4个顶级的学术会议，分别是 FPGA、FCCM、FPT 和 FPL。我也是这4个会议的 TPC 成员也就是技术委员会成员。说白了就是义务做会议的审稿工作。具体来说FPGA 这个会是4个会议里绝对的老大，从名字也能看出来它是 FPGA 这个领域的旗舰级会议，没有之一。一般FPGA 领域最顶级的成果都会选择在这里发表。那我自外自夸一下我们做的文章也是发在这里。谷歌学术有个会议和期刊的排名在计算机硬件设计这个领域中 ，FPGA 大会在全球排名第11位，在上榜的国际会议中排名第4。那么 FPGA 这个会每年2月都会在美国加州的蒙特雷举办，用情非常专一，不像其他很多的会议各种地方轮着开。但是呢，我也不知道为什么要选这里。今年非常遗憾，由于一些懂得都懂的原因，我没能去美国现场参会，只能线上做报告，交互感和体验感就差很多了。那么接着说4大会老二是 FCCM， 全称是现场可编程定制计算机会议。有点拗口，但是呢，本质上还是关于 FPGA 相关的技术。这个会在前面提到的那个排名中排全球第20位。FCCM 呢，每年在北美的各大高校巡回举办。我的第一篇论文就发表在 FCCM， 当时去的时候是在西雅图。老3和老4呢是 FPT 和 FPL， 这俩会的水平差不多我个人感觉 FPT 可能会稍微好一点。它呢每年在亚洲和环太平洋地区巡回，去年呢在香港，我去那一年在上海，明年应该是在日本。那么之前还有澳大利亚和新西兰。那么这个有很多的日本和香港的高校和学者参与。那么 FPL 呢每年在欧洲各大高校巡回，去年呢在北爱尔兰，今年在瑞典，我当时去的时候在奥斯陆。如果你是本科生、研究生，想要从事 FPGA 相关的学术研究，或者只是想要了解现在的 FPGA 领域都有哪些最新的研究进展，那肯定就需要关注每年这4个会上发表的论文，基本就涵盖了 FPGA 所有主要的研究领域。好，那么 FPGA 主要的学术研究方向有哪些呢？主要集中在3个领域，一个是和人工智能和机器学习相关的领域，这个在我之前和帝国理工的 Konstantinis 教授的对谈中，他呢也介绍过了，还没看过的朋友们可以去看一看。这个领域主要包括根据 AI 应用进行优化的 FPGA 微架构、设计工具、优化方法，或者是做一些跨学科的结合和应用。第二个研究方向就是 FPGA 作为硬件加速器在云计算或者是网络应用里的一些研究。第3个就是面向 FPGA 的开发工具和语言的研究，比如说高层次综合，也就是用 C、C++、Python 这些高级语言来做开发 FPGA 等等。那么接下来再说说我们这次发表的论文，题目叫做 Encore 基于 FPGA 加速的高效架构验证框架。它主要是用 FPGA 来做硬件加速器，但是呢，我们把它用在了加速芯片验证这个领域，并且做了很多创新的研究。总结来说主要有3个主要的贡献。首先 Encore 框架将 FPGA 加速验证和软件仿真的细腻度调试能力结合在了一起，用于高效的处理器核心架构验证。第二 ，Encore 实现了自动的硬件快照机制，可以在仿真器中复现当前的全部设计状态，从而进行非常细腻度的调试。第三，我们在赛灵思的 UltraScale Plus FPGA 上通过实验证明，和软件仿真相比 ，Encore 框架可以实现超过4.4万倍的性能提升，以及极小的面积开销。 那么具体的研究工作啊，可以看接下来的大会报告，也可以看一下我们的论文。欢迎学术界和工业界的各位专家大佬一起合作，也欢迎对这个方向感兴趣的同学加入我的团队。我常年招实习生，具体的信息呢在下方的评论区里。每年啊，我应该也有硕士生名额，欢迎报考我的研究生。如果你对学术研究类型的视频内容感兴趣，也别忘了点个赞、关注、留言，让我知道。好了，接下来就是我在今年 FPGA 大会上的报告。
Hi everyone, I'm Ken. I'm Associate Professor at Institute of Computing Technology, Chinese Academy of Sciences. It's a great pleasure to present our work at this year's FPGA. Unfortunately, I can't be there in person to join the conference due to the visa issue, but I will try my best to present online. So today I'm going to talk about Encore, which is an efficient architecture verification framework with FPGA acceleration. So why are we doing this, right? So the background is all about verification. We all know that chip verification is very important, especially for functional verification. There's a study showing that up to 50% or even 70% of the entire chip development cycle is all about verification, right? So I was doing verification at Intel for the past few years. And when we were developing products, and verification takes a large amount of efforts and time for the entire chip design or system design. But when we look into chip verification, it's very difficult. It's not an easy job. That's why people develop, a couple of advanced verification methodologies, such as constraint random, UVM, or even formal method to do functional verification. And conventionally, we have FPGA prototyping and even emulation methods. So chip verification is very, very difficult. But when we look into the details of verification, right, so we can find there is an impossible triangle of verification, if you like. First is the high performance, i.e., how much time or how fast can I run a simulation, right? Second is the good debugging capabilities, i.e., how easy can I locate a bug? Last but not least is the low cost, i.e., how much money should I pay? Because either you pay for the simulation software itself, or you can pay for more advanced equipment or hardware in order to accelerate or ease the debugging verification process. But normally, not all these three metrics can be satisfied at the same time. So if we present using assertions like in verification, then high performance and good debugging capability at a low cost, in most cases cannot be satisfied at the same time. So for example, if you want to have good debugging capability and relatively low cost, and this is what most people is actually currently doing, you can use in software simulation like in model sim or UVM or formal methods even. So in that case, you can have very fine-grained visibility of the design itself by looking at the waveforms. It's relatively cheap, and you can perform very low-level debugging of your design. But in terms of high performance, right, software simulations sometimes might be very slow. So in that case, people using FPGAs to accelerate the verification process, but it lacks of low-level visibility of the design in detail. Although conventional approaches like chip scope ILA or signal tap can help to some extent, you cannot rely on them for your proper verification process. You still need to have a look at the waveform. So alternatively, if you want to have high performance and good debugging capabilities, we have industrial solutions like the emulators from Synopsys or Cadence or Mental Graphics, right? So they have very big machines called emulators to help you to maintain relatively high performance for simulation or test. And also when an issue occurs, you can have good visibilities of the design or the bug in detail. But on the other hand, you have to pay for it. And normally the costs of this set of machines are really high and really expensive. So not for everyone to use this type of machines, even though in big companies, not every team have the access to those type of machines. So if we put these three metrics into this axis, right? So I've just got two dimensions. One is the performance, one is debugging capabilities. So you can see if you want to have very high performance, you can use FPGA prototyping, but it lacks of good debugging capabilities. If you want to have debugging capability, you can use in software simulation, but normally it runs very slow. But if you want to have something in the middle, you can use in the emulator, but normally it takes large chunks of money. So that's why we are looking to this direction and why we propose Encore. We would like to see if it's possible to achieve relatively good performance debugging capabilities with relatively low cost in one system. That's what we are going to talk about today. So the main contributions of Encore is threefold. One is that we develop a verification framework specifically targeting processor verification. So in Encore, we're using FPGAs to accelerate the verification process, and also we incorporate fine-grained debugging capabilities. That's why you can achieve performance and good debugging capabilities at the same time. Specifically, we do automatic checking on a single FPGA SoC, i.e. an FPGA with programmable logic as well as hardened ARM processors. And we implement RTL design to software reference model on the same FPGA, so we can perform automatic checking on the fly during runtime in relatively fast. And also we enable hardware snapshot based on some previous work called State Mover from University of Toronto. And we can trigger the snapshot automatically once potential bug is found. And we have done a couple of extensions and optimizations of the previous work. So in the following of this talk, I'm going to talk about what is Encore, including the key architecture and software modules within Encore, as well as the whole picture and its workflow. I'm going to talk about a simple debugging example, like how we're using Encore to identify a bug within a processor or CPU design. I'm going to talk about the performance of using Encore in terms of area and the cost of time, and also give my conclusion at the end of this talk. So in general, let's look at the hardware architecture, right? So like I said before, Encore is a verification framework with FPGA acceleration. So in this paper, we are targeting processor verification for some reason I'm going to talk about later. But with FPGA acceleration, we can achieve relatively fast speed for verification, as well as fine-grained debugging capabilities. So we're using a chip, something like Zinc, right? So we all know this type of FPGA SoC has a reconfigurable fabric for programmable logic, as well as hardened processors, normally ARM processors. We can implement the RTL design directly on the reconfigurable fabric, as well as the reference model, which is normally written in C or C++ or high-level languages in software. So we implement that in the hardened processors. So both of them can run simultaneously on the same FPGA. But in order to do automatic checking, so in that case, we develop software monitors and drivers and from the reference model. And we're not actually looking to all the signals in the hardware. We can extract or identify key signals from both software and hardware. So for example, in processor designs, we can look into the key registers, for example, the program counter or some CSR registers. And so they will change once they running the instructions. And we monitor those key registers or signals on the FPGA. And we develop, compare, and checking logic in hardware. So both of them, so the signals from the hardware and signals from the reference model can be compared simultaneously when running the program. So if they run with the same results, right? So you can continue with your program, but if there's a mismatch found, which indicates something might go wrong. So yeah, so in this case, we use a RISC-V processor, which is open source processor called Nutshell. And also we're using the ISA emulator, which is called NEMU, which is running on the ARM processor hardened on the FPGA. The ISA emulator is the emulator for RISC-V, right? It's not specifically designed for Nutshell or other RISC-V processors. It's designed specifically for RISC-V instruction set architecture. So basically, you can change the design on your fabric. You can replace Nutshell on the left-hand side to, for example, Rocket Chip or from Berkeley or from other universities or even your RISC-V designs without changing the emulator on the right-hand side because it is ISA specific emulator. So if we look into other part of Encore, which incorporates an external memory, so in that case, we have a test program, which is a set of benchmarks like a micro bench or other type of benchmarks was saved on DDR. But we run the same test program on both hardware and software. So they run the same set of instructions, and they have synchronization schemes between the hardware and the software to make sure they run and check and compare the results from the same set of instructions. And other than that, we have separate address space for both the hardware and the software. Both the hardware and the software are running the same program simultaneously, and normally, if nothing goes wrong, they will reach to the end, and the results in the checking logic will, saying like there's nothing actually mismatch is found. But in the interesting case where you find a mismatch in the checking logic, i.e., the potential bug is found, we have incorporated another scheme called hardware snapshots. So in that case, once the bug is found, we will take the hardware snapshot of the entire FPGA chip, the programmable logic part. So we'll record the state of every single signals, like the LAT outcome, the registers, the memory, into the hardware snapshot. And we will also record the memory data in the DDR as well. And we will reconstruct using that type of information and reconstruct the simulation in external simulators, software simulators like ModelSim. So we can do very fine-grained simulations and stuff. So this part of work is extended from a previous work called State Mover, which is from University of Toronto, which is a very good work. So Encore uses State Mover as the simulation backend, and we have done a couple of optimizations. We extend State Mover to more advanced UltraScale Plus devices. Originally, State Mover was built on UltraScale devices. And also, we have included some reference models for simulations for external devices, something like DDR and JTAG and so on. We got two layers of accelerations of Encore. First is to using FPGA to accelerate it naturally. So in that case, when you compare against software simulation only approaches, so FPGA-based implementation can give you relatively fast simulation speed. But on the other hand, we noticed that there's multiple levels of abstraction in processor or in digital circuits designs, from gate level to unit level, microarchitecture level, or ISA level, right? So like I said previously, we're using ISA level simulation instead of gate level or RTL level for our simulations, because more abstraction level, the higher speed like you can achieve. So for processor designs, in many cases, you not necessarily need to know the design details when you're trying to find the issue, right? So you just need to run a bunch of benchmarks and see if there's some kind of interesting or dodgy behavior like you can find during the simulation. But once this, so that in that case, you want to reach to a bug as fast as possible. But once the issue is found, you want to have very fine-grained details of design. That's why we have the hardware snapshot to export everything, and you can see all the details and all the signals in ModelSim. So I'll give you a quick example of how we design or debug a 64-bit RISC processor. So like I said, we're using Nutshell as the example of our processor design. It's an open source 64-bit RISC-V processor. Everything is open source, so you can play with this. And the architecture diagram is shown on the figure on the left, on the right. So Nutshell is not a toy per se, right? So it's more of a similar levels of the Rocket chip, if you know from Berkeley, from the similar level. It's capable of booting Linux and do some basic functionalities using Nutshell. But in these diagrams, as you can see, we will monitor the key registers, including the PC register, program counter, and some of the CSR registers in Encore. But in simulation, there's no need to identify any of these registers, right? Like I said, Encore has the capabilities to see all the design details. So you just need to pick the key registers to trigger the error or trigger the hardware snapshot, right? So in the example, we compare the program counter. So step number one is to see if we find a mismatch between the DOT and software emulator running on the ARM processors, like on the FPGA. So if a mismatch occurs, right, we go to step number two, which triggers the hardware snapshot. And it will also identify some, other key signals or sideband data, which is, for example, in this case, is the instruction counter. And step number three is to use the sideband data as information to identify, to do some debugging, really. So you need to identify the corresponding instructions in the simulation. For example, I know the instruction counter is 1505, so I'll find the specific instructions and have a look at the and have a look and debug. So in this case, we know like this is a jump instructions. It is modify A4 register. But in some cases, right, it may not be that specific state or instructions. You may need to trace back to the root cause. For example, it changes the jump instructions actually modifies the A4 register, which contains the wrong data. You may need to trace back to see which instructions actually changing or modifying this data in the first place. So in this case, we can see this is a logic shift instruction which modifies this instruction which goes wrong. So in terms of the performance of Encore, like we first compare with the conventional debugging approaches like IOA, the integrated logic analyzers. So for the conventional approach, you have to recompile your design when adding new signals, right? But for Encore, like I said, there's no need to recompile. So we compare two configurations. One is to include PC, a program counter, and one CSR register. Configure 2 is to include PC and 32 CSR registers. So we compare the area consumptions of both approaches. As you can see, for configure 1, Encore consumes smaller area than the IOA-based approach. But if we want to have a look at more registers, right, 32 registers, IOA consumes a large area overhead in comparison to Encore. So in terms of the performance, right, so first we compare Encore with FPGA prototyping only and software emulation only approaches. So the blue bar is for Encore. As you can see, if for those type of benchmarks, Encore is slower. This is expected, right? Because we introduce overhead for checking and synchronization between software and hardware, and we do hardware snapshots when the bug is initiated, like the FSM, all that kind of stuff. So Encore is slightly slower than those type of approaches, but don't forget, FPGA prototyping doesn't have the low level or fine-grained visibility of your design. It is fast, but you can't use that for debug. So software emulation is something like we run on the processor at the ISA level, right? So you can't debug the microarchitecture related details. So we compare to software simulation, which has the very fine-grained visibility of your design. But as you can see, Encore is much faster than software simulators. So this means you can reach to a bugging state relatively quick. You don't have to wait for this long hours before you reach to a certain interesting state. But you can reach to that state really fast using Encore. And then you can offload everything using the hardware snapshot schemes and doing the fine-grained debugging. So in conclusion, Encore is a verification framework. So in this paper, we're targeting processor verification, but the general idea can be applied to many types of applications. If you have a DUT, you have a reference model, you can put them into the Encore framework. And it combines the FPGA accelerated verification and fine-grained debugging capabilities. So you can achieve the performance and good debugging capabilities at the same time. So Encore performs automatic checking on a single FPGA SoC. So you take advantage of the FPGA SoC, which combines the programmable logic and hardened processor at the same time. So you can implement your RTL design and software reference model on the same FPGA. And we have developed a specific hardware to do the checking on the fly. And we can take the snapshots and offloading it to the software simulators to do further debugging. So Encore is relatively fast and is capable of fine-grained debugging. Since it's using FPGA, it is with low cost. So somehow it can achieve those three metrics at the same time. So finally, a quick introduction of the team. So I'm Ken, like I said, I'm from Institute of Computing Technology, Chinese Academy of Sciences. So Shuxiang and Yuhan were doing the internship with me, and they from Shanghai Tech University and Imperial separately. And David is my long-term collaborators, and he's from University of Sydney. Professor Yunga Bao is my colleague from Institute of Computing Technology, Chinese Academy of Sciences as well. So big thanks to the team who does this great work. So yeah, that's all from me today. Feel free to reach out if you would like to use the Encore or you would like to collaborate. And I'm hiring actually. Postdocs, FPGA engineers and interns are welcome. Please email me your CV. Feel free to check out my webpage and feel free to subscribe my YouTube channel. I'm a part-time YouTuber. It's a great honor to present this work, and I'm happy to take any questions you may have.